Thank you very much.
We will start in a while, so please be with us.
Can you hear me fluently?
Yeah, sure.
Oh, okay. How about weather over there?
Yeah, it's nice.
Nice, huh?
A bit warm, but otherwise it's nice. Today is a bit cloudy, so
It is a bit warm. Here also there are hello, Utpal.
Yes. Hi.
Good morning.
Morning.
Nice to see you again.
Yeah. So it's 9 o'clock, right? Or 9:40. In your place, it's 9:40, right?
9:42. Yeah.
Yeah. And everything is oil now. Uh, maybe.
Hello, Gautam da. Hello,
Hello.
Utpal, are you hearing me?
Yes.
Okay.
Perfect.
Hello.
Yeah.
Hello,
Yeah.
hi. I'm Achinta from Bose Institute, Kolkata.
Very nice to meet you. I'm Mehdi.
Very nice to meet you. Yeah.
It's a pleasure to be here.
Thank you.
welcome, Professor Singha.
Hello. Yeah. Thank you.
Oh.
Good morning, everybody. So, with the permission of Honorable Vice Chancellor, we are now starting our webinar series on advancements in condensed matter physics. SCMP 2020. Professor Dilip Chandranath, our VC, is presiding over this session. Sabrina Paul, on behalf of the Department of Physics, Assam University Silchar, welcome you all to this event. Now, may I request Dr. Utpal Sarkar, convener of SCMP 2020, to address the web gathering. Sir, please. Hello, sir. Hello, sir. You are muted, sir. Hello, Utpal, sir. You are muted.
Okay. Hello. Now, are you hearing me?
Yes, sir. Yes, sir. Now it's
Yeah.
fine.
Okay. Honorable Vice Chancellor, Professor Dilip Chandranath, Dean School of Physical Sciences, Professor C.R. Bhattacharjee, Head of the Department, Professor Atri Deshmukh, Resource Persons, Professor Mehdi, Professor Manna, uh, uh, Professor Singho, Professor Mahato, my colleagues and dear students. A very good morning to all of you. As a convener of this program, I welcome you in this web gathering. I am immensely happy to get a chance of organizing this two-day webinar and based on the ongoing pandemic. It's a glorious moment for us as we are celebrating the 25th anniversary of the Department of Physics, Assam University Silchar, and this international webinar, Advancements in Condensed Matter Physics, is a part of this grant. I am really happy that in this international emergency period, 4 eminent scientists have joined with us to share their work. I am sure that master students, research scholars, and early stage researchers will be highly benefited from this webinar. These lectures will be definitely helpful in the long run. I thank Professor Deshmukh for her support. I must thank Dean School of Physical Sciences, Professor C.R. Bhattacharjee, for his encouragement. He actually suggested me to organize such an event. I am extremely thankful to Chief Patron and Honorable Vice Chancellor of Assam University, Professor Dilip Chandranath, for his continuous kind support. Today, on the 7th August of 1941, Rabindranath Tagore passes away. So, to remember him and being an alumni of Viswabharati, I would like to conclude my deliberation with Tagore's quotation, "Science urges to occupy by our mind the immensity of the knowable world. Our spiritual teacher enjoins us to comprehend by our soul the infinite spirit which is in the depth of the moving and changing facts of the world." Thank you.
Thank you, sir, for your words. Now may I request Professor Atri Deshamukhya, Chairperson of ACMP and Head Department of Physics, Assam University, to address. Ma'am, please.
A very good morning to all the participants. We are having almost around 400 participants, some inside this WebEx platform, some YouTube live. I also welcome the eminent speakers, Professor Mehdi, Professor Manna, Professor Mahato, Professor Singho. I am really thankful to you all that you could spare your time to be here with us in this international webinar, which I hope will be very fruitful for the students to attend. And as the convener already said, we are celebrating the Silver Jubilee, and this is the second program, and we are planning to organize different academic and cultural programs during this whole year. And I hope we'll be successful in our endeavor. And I thank everyone associated with the event. Each and every member is important. And I also would like to take the opportunity to thank Nayanjyoti Mojumdar from Department of Computer Science, who has helped us a lot to make this technical part working fine. Thank you all. Devolina.
Thank you, ma'am, for your kind words. Now, I request the patron of SCMP and Dean School of Sciences, Assam University, Professor Chiraranjan Bhattacharjee, to say a few words. Sir, please.
Honorable Vice Chancellor, Professor Dilip Chandranath, Professor Atri Deshmukh, Head Department of Physics, Dr. Utpal Sarkar, the convener, esteemed invited speakers of this international webinar, Professor Mehdi from Iran, Professor Rudra Shekhar Manna from IIT Tirupati, Professor Achinto Singho, Dr. Sanjay Kumar Mahata, Deutsche Elektronen Synchrotron, Hamburg, Germany. Colleagues, staff members, scholars, and dear students in the department, colleagues from allied departments in the university, dear participants from various academic institutes, I extend a very warm welcome to this international webinar on advancement in condensed matter physics, being conducted by the Department of Physics under the Albert Einstein School of Physical Science. Webinar apart, this occasion also coincides with the celebration of the Silver Jubilee year of the Department of Physics. Established in 1996 in a geographically remote corner of the country, the department today has achieved a stature to reckon with. Students and scholars passing out from its portal over the years have found space across the nation and world, contributing domains. I congratulate the entire department, faculties, scholars, students, and staff who are witness to this historic milestone. I also recall the contribution of the founding faculties and many others for their manifold contribution to take this department to a new height. The title of the webinar, Advances in Condensed Matter Physics, is in itself a very significant theme. Recent progress on topological materials are believed to have great application potential in spintronics, quantum computation, electronic devices of the next generation. More recently, the discovery of the synthetic metallic crystals, tantalum arsenide, as the well semimetal is an important breakthrough. Quantum spin liquids are exotic quantum states of matter that also attracted tremendous attention, both from fundamental point of view and prospective relation with high temperature, superconductivity, and quantum information applications. Fusion of experimental with computational efforts has remarkably advanced condensed matter physics. Scanning tunnel in microscope and density functional theory calculations have completely renovated our understanding of water structure. Condensed matter physics forms the theoretical basis of material science. In the recent decades, the sophisticated nature of these bulging field has led to a bonanza of condensed matter physics are to forecast and perceive novel phenomena properties. Today, condensed nature and electrons regulate physics occupies a unique niche. Progress in this field are extremely important for scientific advancement and for enlightening our ultimate understanding about the nature of materials. Rapid growth in condensed matter physics in the area of scattering, photonics, advanced material, surface analysis, low temperature functional electronic systems, structure of biological chemistry, and high temperature superconductors are noteworthy. The field of condensed matter and material physics imaging in the atomic scale, nano microfabrication, and computing, etc., are very important advancement. These competencies offer prospects to scrutinize the nature of materials at complex with degree of microscopic control that are exceptional. The modern era has revolutionized the systematic technological advancements in preparing materials with exotic properties. Understanding the basic concepts and techniques in the optoelectronic process provide information about the assemblies of multifaceted atoms and multi-component materials. Phenomena of non-equilibrium, biological ideologies will stimulate improvements in technological scale from micro, nanoelectronics to structure of materials to the field of medicine. Immense possibility exist for groundbreaking advancements in condensed metaphysics that will address the national security, economic growth, and quality of life. No great thing come out of the blue. With the sustained effort from the continuing inflow of the talented young scientists and the growing effectiveness of the research community, we look forward to more and more pioneering achievements in the domain of condensed metaphysics in the years to come. Thus, I candidly believe that this webinar being organized in this critical time, severely affected by the global pandemic, unseen ever before, will inspire the new generation researchers profusely. Wishing the webinar a grand success, I once again heartily welcome you all. Thank you.
Thank you, sir, for your precious words and such an informative speech. Now, may I request our Honorable Vice Chancellor, Professor Dilip Chandranath, to address the gathering. Sir, please.
Namaskar. Good morning to everybody. Am I able? Because before that, hardly we am able to hear Professor Bhattacharya. Are you hearing me now?
Yes, sir.
Yes, sir.
Okay.
Yes, sir.
Now it's okay actually, but last part of his speech we heard. Before that, some difficulties. I don't know, only my part or others. So it's a pleasure for me to be here with you in this international webinar on advancement in condensed matter physics. I first congratulate the team physics led by the HOD and other persons like Dr. Utpal Shekhar and others belonging to the same department for organizing this webinar. I understand this is a part of their Silver Jubilee program. And we have with us many resource persons. I understand two resource persons, Professor Singhai and Dr. Mahata, and Dr. Manna, Professor Manna, and other faculty members of this university, students, especially students, because they will be benefited most, and participants from different parts of India or outside India. Yeah, the webinar or some other way, the COVID made it possible for us, for a large gathering and from different parts to hear the same webinar and participate and discuss. Definitely, we are passing through very difficult days. We don't know how long. It's again a random phenomenon, but maybe another few months, maybe we have to pass through that, and then we'll come out of it. So education is a real problem, but some thing we are overcoming. We are finding the new way. We are searching for the new way, like this webinar. The seminar, the physical seminar, has been replaced by the virtual seminar, and some difficulties, technical difficulties are there, because in the initial stage I find that I could not hear the deliberation of the Professor C.R. Bhattacharya, the Dean of Physical Science. He is also here with us. And so anyway, but we are overcoming it and we face the problem. and so is physics here. This is a important, the area of physics, condensed matter physics, possibly the largest area of the physics, the science which is contributing basically our day-to-day life problem, taking care of this, the what science they talk about and the technologies, provide through their innovative thinkings, solving our day-to-day life problem. So now we are facing more problem, different types of problem, and the COVID situation and the post-COVID. So accordingly, I think this science, the condensed matter physicists can see and what are the requirements of the present society, and they can do research on that area and provide a solution to the innovative thinking. So that will be the good contribution of such kind of webinar. I understand the students of the departments or other place, they will be mostly benefited. The research scholars will be mostly benefited. They will be
I can't hear.
Yes. Here, I think
Could
some
you
internet
hear,
issues.
Professor?
No, sir. No, sir. No, sir. I also can't. I think some internet issues are there. I think there is some internet issues, so we cannot hear him.
Hello.
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 Dovlina, you tell document to professor or something what to do regarding.
Hello. Hello.
Hello. Who was speaking?
Hello. Hello, sir.
Dovlina,
Uh, yes, sir. Yes, sir.
Dovlina, you are addressing someone.
No, we can't listen to VC, sir. Actually, it is disconnected, I guess.
Please wait a little. Please wait a little.
Oh, okay. Okay.
Window binding.
Devolina, you can continue. Campus Connect has gone, university is disconnected. You continue.
Okay, okay. So,
Devolina, you please continue.
okay, man. Okay. Okay. So, end due to the issues. So, I thank him for his valuable words. Now, I would like to request Dr. Mahananda Baro to give the vote of thanks. Mahananda sir?
Audible? No?
Yes, sir. Yes, sir. You
Am
are
I?
perfectly audible.
Am I? I'm just switching onto my video.
Yes, sir. You are audible.
Yeah. So, all, I am honored in the vote of thanks for this event to the dignitaries present here. First of all, I'd like to propose hearty vote of thanks to our chief guest, Professor Dilip Chandra Nath, Honorable Vice Chancellor, Assam University, for gracing today's webinar. Thank you, sir, for your very interesting and thought-provoking address. I'd like to express my profound gratitude to the Dean, Albert Einstein School of Physical Sciences, Professor C.R. Bhattacharjee, for his nice words. I'd like to thank the invited speakers of the technical sessions, Professor S. Mehdi, Professor Rudra Shekhar Manna, Professor Ashinta Sinha, and Dr. Sanjay Kumar Mahata for attending this inaugural session. I'd like to thank our beloved HOD Madam, Professor Atri Deshmukhia, for her support and guidance. I'm happy to express vote of thanks to the organizers and the faculty members of the physics department. I'm very much thankful to Mr. Nayanjiti Majumdar, Computer Science Department, Assam University, for the technical support. Last but not the least, I'd like to thank the participants for attending the inaugural session. Once again, I thank one and all present here. Thank you.
Thank you, sir, for your words. So, formally, our inauguration program is over with this. Now we are entering into the first technical session. The first talk will be delivered by Professor Syed Mehdi Vaiz Alai. Professor Syed Mehdi Vaiz Alai is working in University of Tehran. He did his master's at University of Science and Technology, IUST, Tehran, Iran from 1999 to 2001. He completed his PhD from Institute for Advanced Studies in West Asia 2007. He was a research assistant at Surface Physics Lab SU in 1999 to 2002, then again at IUST from 2002 to 2003, and at IASBS between 2003 to 2007. He was 2 times junior associate and 1 time regular associate in the Abdas Salam International Center for Theoretical Physics ICTP Trieste, Italy. He is interested in working on computational condensed matter physics. Besides, he is also working on complex systems, nanoscale heat transport, wave propagation, and many more. His expertise in numerical simulations of various systems. His quality of research is manifested through his publications in high-impact journals like Physical Review Letters, Physical Review B, Applied Physics Letters, Scientific Reports, etc. Now Professor Mehdi is going to discuss on the phononic heat transport and thermal rectification in low-dimensional structures. Sir Mehdi, please.
Hello to everybody. Thank you for introduction, and I would like to acknowledge the invitation for this nice webinar. I hope this could increase or exchange between the two countries. Actually, and exchange and start collaboration between the two universities as well as researchers from two countries. Do you have my presentation slide?
Yes.
Hello?
Yes, sir.
Yes, sir. Yes, sir. Yes, sir.
Okay. Okay. Do you have also my pointer as well?
Yes, sir. Yes, sir. It's fine.
Okay. Today I will talk about phononic heat transport and thermal rectification in low-dimensional structures. Before starting, let me introduce a little bit about my country and sightseeing places. We hope to have all of you someday Iran. Let me. Is it full screens or not?
Oh, sorry.
Presentation
Now
mode?
it is. Now it is. Yes, sir.
Okay. There are many old places as well as new buildings and new tradition in Iran, and I would like to invite all of you to visit Iran, hopefully after COVID-19 decade. I am working in University of Tehran. There are about 2,000 faculty members and 53,000 graduate and undergraduate students. There are many departments, actually about 120 departments on different disciplines. And I am working in Department of Physics at University of Tehran. I have a group on computational condensed matter physics. We are working on heat transport, mass transport, some sort of statistical physics modeling, as well as dynamics and order disorder properties in granular materials. The outline of talk has been designed. I would introduce to you a little bit, talk about motivations and why low-dimensional thermal transport is important. Yes. Afterward, I will try to give some insights about different approaches is possible to use in field of non-scale heat transport. And finally, I will try to give some insight about results that we have obtained on interface thermal resistance, tuning of thermal conductivity in different structures, the importance of layered heterostructures in low-dimensional cases, and anisotropic heat transport in low dimension. If I would start from one point of view, it is two possible challenging problems in heat transport. The first could be direct transformation of heat to electricity, and the second could be heat management. You should be familiar with thermoelectricity, the direct way of transformation of heat to electricity. It is the inverse of Peltier effect, that by imposing electrical current, it is possible to create heat. On the other side, it is possible to directly transform heat or temperature gradient to electric voltage. There are good possible candidates or materials for this purpose, but for characterizing the efficiency of a given material, a ZT parameter has been introduced, a dimensionless parameter. It is proportional to the power of 2 of Seebeck effect. It is proportional to electrical conductivity, the temperature of the system, and inversely related to thermal conductivity. It is important to mention that thermal conductivity could be carried out by different carriers. For instance, it is possible to have electric thermal conductivity, phononic thermal conductivity, magnonic thermal conductivity, and so on. And all of them have been considered here and plays important role. For a good material, ZT or figure of merit should be higher than 1, and the goal and ideal magnitude is larger than 2. People has been tried to use this idea and introduce different good thermoelectric materials, but we know that if we have a very good electrical conductor, thermal conductivity might be high. And it is a competition between the killing thermal conductivity and increasing electrical conductivity. This is the power factor, the Seebeck effect times to electrical conductivity, and the inverse value of thermal conductivity. For an example, bulk silicon exhibit a low ZT value, about .01, because it has very high thermal conductivity. And one possible way of having silicon for thermoelectric effect, it is needed to kill thermal conductivity. And by decreasing the size of the system, as I will address in a few slides, it is possible to kill thermal conductivity and increase the figure of merit parameter. But it is not sufficient since the ideal value is higher than 2. What is the thermal conductivity? We know from Fourier law that if we consider the energy flux, thermal energy flux over the area is proportional to the temperature gradient, and the coefficient is called thermal conductivity. This could be considered for different cases, and here we talk about this value. We know that by decreasing the size of the chipsets, it is possible to have many calculations, but the bottleneck is the amount of heat created or dissipated unfavorably by chipsets. As you see in this graph, by increasing the number of chipsets in the CPU, the amount of dissipated energy increases, and it is somehow going toward to the rocket nozzle in future. But many people try to introduce some kind of systems to decrease to dissipate thermal conductivity, to dissipate this value of unpleasant heat. As indicated here, this is the Intel's power density. By increasing the speed of chipsets, the bottleneck exactly correlated with the amount of heat dissipated in the system. This shows how correlation between the clock speed and dissipated power prevents different companies from creating very, very fast computers. In the same time, many effort has been devoted to removing the thermal unpleasant amount of heat from different systems. It means that in addition to have high and low thermal conductivity, it is needed to manage heat flux inside the system. In conclusion, I can say designing high and low thermal conductivity are favorable, but management of heat is also important, and we should consider about the role of low-dimensional structures in both cases. I mean, for the case of heat management and for the case of transformation of heat to electrical power. Why low-dimensional systems are good? Since we have both high and low thermal conductivity with the same structure. For instance, consider graphene case. We have very high thermal conductivity, somehow near to diamond, 4,000 watt per meter Kelvin. And by the same structure, almost the same structure, we have silicon very, very lower values. It means that in case we could hire or use this kind of structure in different systems for introducing very good, possibly thermoelectric device, and also possibly high thermal conductor to remove unpleasant magnitude of heat from the system. Why we are more interested in phononic case? Since for many cases there are phononic dominated heat transport. For instance, for the case of graphene, it is shown that at most about 10% of heat could be carried out by electrons, and most of the heat is carrying by phonons. It means that considering phonons and calculating thermal conductivity of phonons is very important. But by decreasing the size of the system, what happens? In this case, if we consider a diffusive heat transform, we will have a natural mean-free path for phonons. But by decreasing the size of the system, for instance, if we create a thin film or a superlattice and so on, the magnitude of phonon mean-free paths will be decreased. This is somehow a relation to show the effective mean-free path of phonons, which means that by decreasing the size of the system or eliminating a specific material in a specific structure. For instance, I mentioned about silicon and using instead silicon nanowire. It is possible to decrease thermal conductivity of system, but it's not the whole case. If we have a boundary at a given system, boundary means that if we have a complete lattice at left and one the same at right, but different material, for instance, by changing the atomic weight of material, atomic mass of material at the two sides, the vibrational density of a state of phonons at the two sides of the system becomes different, and heat carriers from the left to the right will be scattered at the interface. This This feature is called capital resistance of interface, and it is very important issue in considering and decreasing the size of system and going toward low-dimensional system. What happens if we have an interface? We have capital resistance, as you see here. If we put hot and cold heat path at the two sides, following the Fourier law, we consider a very flat, very straight graph from the hot to the cold. This is the temperature profile. But at the interface, we have a gap called capital resistance. Something happens due to the phonon scattering at the middle of the system. But I would emphasize that it is different issue rather than the contact resistance. If we have two materials with mismatch interface, there would be resistance, thermal resistance at the interface, but it is completely different rather than what I mentioned before as capital resistance. The value is lower than the magnitude of mismatch contact resistance, but in spite of having a very low magnitude of thermal resistance, it is very important in low dimension. This issue, the interface thermal resistance, has been hired to use in thermal management and managing heat transport in systems. Managing heat transport, I mean, is it possible to have thermal diode or not? This is the case that I am going to address. We know that electrical diodes has been used widely a long time ago, but we have no thermal diodes nowadays, or it is not common, at least. But the idea was proposed at 1935. The method of designing a thermal rectifier, but inventing a thermal rectifier was not quite well established up to the paper of Giulio Cassetti and his colleagues that showed that it is possible to use interface thermal resistance and use the idea for proposing thermal diodes. By proposing thermal diodes, it means that if we have hot and cold region at the two sides of the system, but some sort of anisotropic or nonlinear, as well as anisotropic potentials at the two sides of the system, it is possible to have a thermal diode as it is seen here. Let me talk about the idea. If we have materials with different vibrational density of states, depending on the temperature of material. For instance, at the material A has this profile at high temperature and this profile at low temperature, okay? And if we change the direction of system and we design a system that has the same value of phonon frequencies in one direction and dissociate the phonons profile in opposite direction, it is possible to create a thermal rectifier. The idea proposed and a magnitude for thermal rectification introduced when we have J plus in positive direction, and J minus the magnitude of current in inverse direction. If they are not equal, it is possible to have a thermal rectifier in a given system. A few years later, it experimentally observed in Majumdar group, I think, that it is possible to have a mass-graded nanotube with kind of amorphous graded material, and it is possible to have thermal rectifier in the system. Afterward, many theoretical efforts has been devoted to show is it possible to have good thermal rectifier, and how much is the value of its value. Could be 10%, could be 100% and more, but it is for this paper it was almost 5% of thermal rectification. Different papers showed that it is possible, and it is possible to have high thermal rectification factor, and it the idea opened opened that it is possible to manage thermal conductivity in low dimensional systems. It was very good idea, and people started to work, and I will show a few results from our group. I try to somehow motivate you about the importance of thermal conductivity problem, as well as showing the importance of heat management in low dimensions. But what could be carried out by calculation or computational physics. I would emphasize that it is an interdisciplinary issue. Actually, the number of researchers in this field come from different disciplines: mechanical engineers, physics, chemistry, material science, and so on. There are different groups who are working on heat transfer. As well as considering phonon, there are other groups who are working on photon, magnon, electron. Even for a group has shown how we could have a good thermal rectifiers with phonons and magnon. It was 1 or 2 PRL, I think, to show it is possible to have magnon, thermal rectification, and so on. Now I will try to show what kind of approaches could be hired for this kind of calculation. For heat transport, there are many different approaches to be used, but it depends on interested problem. For instance, if we are interested in this kind of capital resistance and nonlinearity, it is the molecular dynamics simulation is very good, but green copoformalism is not good, and so on. Here I borrowed a slide from Professor Wang's presentation to show that there are different approaches could be possible for calculation of thermal conductivity and investigating possible structure for thermal rectification. What we are working on is almost DFT calculations, as well as molecular non-equilibrium and equilibrium molecular dynamic simulations. Molecular dynamic and non-equilibrium and equilibrium molecular dynamic simulations that we are working, we use LAMS package. For ab initio calculations, we use different packages, and you know that there are different codes for calculating phononic heat transport, and heat transport this part with DFT calculation is very time consuming, but accurate. Are you hear me?
Yes, sir. Yes, sir.
Yes, sir. Yes, sir.
Okay, it is good to have a response that I am.
Yeah, there is no
Yes,
problem.
sir.
Okay, thank you very much. Okay, for non-equilibrium molecular dynamics simulation, you should be familiar with molecular dynamics simulation. It is needed to have hot and cold
Interacting audience.
interacting audience. From one side to the other side, and if let the system to be obtain its STD state, it is possible to measure the value of heat current, and again it is possible to measure thermal conductivity. For this case, for the case of non-equilibrium molecular dynamics simulation, it is needed to create one system consists of hot and cold. It is possible to have just one case with a rigid body, but it is better to have a complete periodic boundary condition and have cold and hot heat passes at two sides of the system. In this case, we have almost two linear profile, and with this two linear profile, it is possible to calculate this temperature gradient. We have the magnitude of area, and it is possible to calculate heat current. It is possible to measure thermal conductivity. But it is not the case, as I mentioned about the size effects in low-dimensional system. In this kind of system, it is needed to calculate finite size, to consider finite size scaling as well. And by increasing the system size, it is possible to remove the size effect. It is needed to simulate this structure in different sizes and extrapolate the magnitude of 1 over kappa versus 1 over L of Z, the length of a scale, and it is possible to find the magnitude of thermal conductivity of this system comparable with experiment or bulk. For the other approach for DFT calculation, there are other linear Boltzmann transport equation, as well as in different approaches. For instance, relaxation time and iterative methods that has been considered for measuring or calculating thermal conductivity. Most common packages are PhonoPy that could be worked with different packages, for instance, FHI AIMS, VASP, and Quantum Espresso, and so on. And it is possible also to use ShaneBT or AlmaBT that has been developed for measuring, calculating thermal conductivity of a given, phononic thermal conductivity of a given system. Now I will try to talk about results that we have obtained from different point of view. The first was how to introduce a good thermal interface resistance and hire it to have a thermal rectifier. For this case, we used three different systems: graphene hybrid monolayer, hybrid carbon nanotube and hydrogenated carbon nanotube, as well as multiple carbon nanotube. We showed that in this kind of system it is possible to have thermal rectification, and also we studied the effect of boundaries at grain boundaries at thermal conductivity of graphene and creating capital resistance. The first case was the case of graphene and graphene interface. As it is clearly seen, it is possible to have pristine graphene and hydrogenated one. In this case, it is possible to have a capital resistance. It is almost known, but this capital resistance depends on the direction of heat transport, as it is seen. And we try to measure this, and we showed that it is possible to have 22% of thermal rectification. As I mentioned about the vibrational density of the state of the system at the two sides, I mean right and left, it is clearly seen how this hydrogenation affect on vibrational density of a state, which means that phononic heat transport affected by this hydrogenation. We showed that it is not the case of length scale. By increasing the length of the scale, it is also possible to get almost the same value of thermal rectification. For this case, we carried out the same idea for the case of carbon nanotube, but in this case we showed that the different percentage of hydrogenation could be higher as well. For 25, 50, and completely hydrogenated part of system can create also a capital resistance at the interface. The capital depends on the direction of the temperature gradient, as well as the magnitude of thermal rectification is almost better than graphene system. This figure also shows the effect of hydrogenation at the two sides of the system. The other issue, the other problem that we consider was not transport through layers, but normal the layer. If we considered radial thermal transport in multiple carbon nanotube, we consider the hot and cold heat passes and inner and outer walls in multiple carbon nanotube as indicated here, and we measured the magnitude of thermal conductivity and showed that it is possible to have, let me come here, it is possible to have thermal rectification. It is not the case of number of layers. It is possible to have better thermal rectifier by increasing the number of layers, almost a golden number. And it is not the case of the length of a scale. By increasing the length of a scale, it is also possible to have thermal rectifier, as well as the mean temperature of the system. In whole cases, we have almost good magnitude of thermal rectification. Let me say something about the temperature profile in this kind of a structure, since I will address this issue afterward as well. In multiple carbon nanotube, we have very good thermal conductivity inside a tube. But why? Because we have covalent bond between atoms, and it is high thermal conductivity in this direction. But what is the case in between layers? We have a weak Lennard-Jones interaction or van der Waals interaction between layers, which means that the amount of heat transport between layers is not too high. Which means that if we consider hot and cold bath to the outer and inner part of the system, we will have almost a flat temperature profile inside each layer or inside each tube. But by having larger larger almost mass rather in outside rather than the inside, it is possible to get thermal rectification in this system. It was interesting issue that I will come back to it a few slides later. We also investigated the capital resistance at the interface at grain boundaries in graphene, and we showed that the grain boundary, in spite of that, the fact that the heat transport in graphene is not directional, it is isotropic. In large system sizes are isotropic, but in low dimension, we have capital resistance due to this grain boundary at interface, and the magnitude has been shown here. This was the interface thermal resistance and thermal rectification. The other issue that we were interested in was layered materials, as indicated in the case of multiple carbon nanotube. In layered material, it is an important issue that is there a capital resistance at interface or not. We investigated this case if we consider hot and cold heat baths at the two sides of the system and calculate this kind of averaging, you will get a very nice capital resistance at the interface. But it is not the case. Since, as indicated in this figure, the temperature profile inside a two-dimensional or a nanotube structure is very high. It means that the temperature will be transferred easily in upper layer. But the amount of thermal heat transferred just via very weak Lennard-Jones interaction, which means that there is no equilibration at here, and it is not possible to average two different temperature profile with each other. We could say that the temperature of the system is this value if we have a Boltzmann Maxwell-Boltzmann distribution of velocities. But there are two different Maxwell-Boltzmann distribution of velocities in two layers, which means that there is a transport from top to the bottom layer, which means that there is no equilibration. There is just a CDL state, and it is not possible to mention thermal capital resistance at interface. We showed this by very large, by simulation of very large system sizes, about half micron, and showed that there is no capital resistance, and there is a kind of transport from the top to the bottom, and it is possible to write something continuum system. This result has been experimentally verified 1 year later. We also tried to investigate how it is possible to tune thermal conductivity of a given system. One was using the curvature effect. As you see, it is possible to use curvature, local curvature, to decrease the thermal conductivity of a given system. In this direction, there is no change, but in this direction, there is a change in thermal conductivity. There are other problems we address. By nitrogen doping of graphene, it is possible to tune thermal conductivity. Whole things are ways to tune, increase or decrease the thermal conductivity of system. How much I have time?
Yes,
Are you
sir.
here?
Yes, sir. Yes, sir. Sir, you have 10 to 12 minutes more, sir.
10 to 12. Oh, thank you. And also we studied the effect of sp3 bonds between layers, how it is possible to decrease thermal conductivity of bilayer graphene, one of interested materials in low dimension. We showed that by creating sp3 bonds between top and bottom layer, it is possible from experimental point of view with femtosecond laser or electron gun. It is possible to create this kind of sp3 bonds. It is possible to tune, I mean decrease the thermal conductivity by 80%, an 80% factor. Here is the vibrational density of a state of carbon atoms that has no sp3 bond in comparison with sp3 bond. You see that for the case of sp3 bond, the green one, the vibrational density of state has been completely changed. We also investigated bilayer silicon case and showed that how layering in silicon could lead to increment of thermal conductivity rather than decrement. Let me skip a few slides. It is possible to measure thermal conductivity, but for each case, as you see, different available potentials. For instance, a Stringer-Weber 1, a Stringer-Weber 2, and MEAM has different introduce different magnitude for thermal conductivity. This is one reason why people try to give up molecular dynamic calculations and go to density functional theory calculations. It is possible to also investigate the effect of strain on thermal conductivity of a given system by imposing a strain on a given system. It is possible to tune the thermal conductivity as it is seen for the case of biaxial and uniaxial strain. The other systems similar to graphene also be interested by other groups. Blue and black phosphorus, due to the anisotropic structure, was also interested by several groups, and they have published papers. In this case, it is possible to impose a strain in different direction, which means this kind of strain can create a considerable change in thermal conductivity. As it is seen here, for the case of silicene, it is possible to change thermal conductivity considerably by imposing a strain in different directions. We also studied the case of arsenine, the same structure. As you see, it is a kind of buckled two-dimensional structure, the same as phosphorus, black phosphorus. And we showed that it is possible to have anisotropic, highly anisotropic heat transport in different direction. I mean, in this direction and normal to the surface direction, zigzag and arm chain, and it is almost 4 times higher than the magnitude. What is the other possible methods? We try to use, since DFT calculations for instance for this case was very time consuming, we try to use DFTB plus Boltzmann transport equation for measuring thermal conductivity of a given system. And it is another approach, could be hired, but it is not very easy to measure the magnitude of thermal conductivity. I would somehow summarize what I have talked up to here. The importance of tuning thermal conductivity, important for decreasing the magnitude of thermal conductivity, very favorable for the case of thermoelectric effect. Also, it is needed to have nonlinear effects. For instance, the case of thermal rectification, it is needed to have anisotropy or as well as nonlinearity. It is possible to measure things with molecular dynamics simulation. This is an open subject of research. Also indicating the importance of ab initio calculations, but the whole things are somehow nowadays are hired in material discovery. I would say something about material discovery, that nowadays people try to use a kind of material discovery approach to find the best, for instance, power factor, and finally decrease the thermal conductivity by another. Let me acknowledge my colleagues from University of Tehran and the other place from University of California, Isfahan University, Aalto University, and let me talk about just in one sentence that for the case of material discovery, it is needed to find a branch of material and finalize it for a specific purpose. And for this case, we studied to have ultra power factor for this monolayer to use for the case of thermoelectric effect. It is possible to use the same strategy to have the other kind of properties similar, to have very good absorber and so on. Thank you very much for your attention.
Thank you, sir, for such beautiful and informative presentation. Hello.
Yes.
Now the session is open for discussion. If anybody is having any question, you may please raise your hand and unmute yourself. Or you may put it in the chat box also.
Actually, Utpal sir, Utpal Shekhar sir is Radio 1, but I am allowing you to interact with the sir. Hello.
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 Yeah. Professor Mehdi, thank you so much for your very good presentations. I have some query regarding presentations. I would like to know when you are doing Boltzmann transport equations, that time uh, the phononic part is not there, right?
Phononic part is hard to calculate.
With
You
Boltzmann
means that
transport equation.
it is possible to have it's possible by using Shane BT, for instance.
Oh,
There,
yeah.
there are different groups who developed very good packages for measuring heat transport
Yeah, but
with different.
Boltzmann transport is basically classical one. There is
Pardon?
Boltzmann transport equation is BT. BT is basically semi-classical one. Don't consider
Yes.
phononic part, right?
Yes.
Yeah. And
But
another,
it is possible. It is possible to use other kind of distributions, not just
Boltzmann. Okay.
yeah.
And another thing is that what is your experience for doing this phonon calculations? If I use only one single unit cell, if I
Yeah.
use only one single unit cell and do the uh, phonon calculations, and if I
No.
use
It
a
is needed to have super lattices.
super, yes, how long?
Yeah.
How big?
Actually, one approach it is needed to have different curves and have saturation. It is needed to have saturation to get the correct value.
Saturation of
If
what?
if if if, if you in some cases, for instance, in some cases, if you try to obtain dispersion curve, you get some negative magnitude. And if you increase the number of atoms and create a supercell, you can get it better and better, but it is needed to have all of them in one graph and see when they converge in a specific dispersion curve. That's the smallest possible curve, similar to the best, is what we use for calculation.
Okay. And another one is that when you are stretching, when you are giving stress to the system, initially the thermal conductivity increases and then decreases. It reaches a peak and then decreases. In one of the
Thermal
slide,
conductivity
yeah,
can increased,
yeah,
but depending on the anisotropy of the system. For instance, for the case of silicene, we have a kind of buckling
I see.
for atoms, and by imposing an strain at the first, less than a few percent of strain, this this buckling disappears.
Okay, so it becomes planar and the bond will be closer, something like that.
Exactly.
And then
This is the
the
reason
voltage.
why it increase the thermal conductivity. But afterward, by imposing more stress and creating more strain in the system, phonon interaction becomes higher and thermal conductivity decreases.
Okay, okay, thank you.
Thank you very much.
Thank you, Sujit Tiwari sir. He has put it in the chat box. So the question is how to account for the distortions. Sir Mehdi,
How to account
for the distortions.
for
For the distortions.
distortion of what?
I am also allowing him to directly interact with you, sir. Hello, Professor Sujit Tiwari.
Yes, hello.
Hello, am I audible?
Yes, sir.
Hello.
Yes.
I can hear.
During the calculation of thermal conductivity that you mentioned, sir, there may be fluctuations and due to that there may be distortions in the entire lattice and superlattice that you are telling. So how will we accounting for those distortions in the calculations?
Could you
That
please
means
kindly repeat it again?
During this calculation of thermal conductivity of different lattice structures that you have mentioned here, there will be distortions of the structures as well. So how will we calculating those distortions in this calculation?
distortions
For
of
instance,
distribution.
curvature.
Yes,
If you
For instance, curvature.
yes.
Okay.
Then dangling of and buckling of the structures, dangling of bonds that you mentioned. So how will we calculating those things?
Okay. For instance, for the case of can you see the slides?
Yes, sir.
For the case of curvature, it is not possible to have the system with this structure without additional criteria. It is needed to create or fix a number of atoms at the boundary, a few number, to create kind of distortion here. For the case of a sp3 bond, for instance, if you want to create a sp3 bond between atoms, it is needed to decrease the distance between the two atoms by almost by hand. By hand means gradually decrease, and if you use correct interactive potential similar to A-Ribo and so on, by decreasing the distance, it creates a kind of sp3 interaction between two atoms rather than Lennard-Jones one. It is possible to define from the first of at the beginning of simulation, but it is possible to have detachment. This bond could tear if we impose very large additional force. Have I answered your question?
Okay. Thank you, sir. Thank you so much.
Thank you very much.
Sir, some questions have been put by our YouTube live participants also. So one of them we can take by Tharnishan Mondal. What is the reason behind Kapitza resistance and what is the implication of it? Sir, am I audible?
Yes, let me come back to the slides. We know the wave propagation from one side of a string to the other side. If we have a mass graded string, wave at the interface scatter. The contributor or the contributor in phononic heat transport are phonons, and the same thing happens at the interface, exactly here. But if we have the same, if we have the same material at the two sides, the density of a state, vibrational density of a state at two sides are the same, which means that one phonon, the density of different phonons at two sides of the system are not the same, are the same. But if we change the material's property at two sides, the the amount of an specific phonon is not equal to the other side, which means that in equilibration, in that temperature, it needs to scatter that phonons into the others to have its own vibrational density of states. Have I answered? And what the other was its application. The other question was its application.
Hello, Jamulina.
Hello.
I think
Hello. Actually, sir.
Yeah, the other question was its application. Am I right?
Hello, sir.
Yes. Could you hear me?
Yes, sir. Yes, sir. So I can take one question at least now. This is Shoham from Presidency University, Kolkata. Professor, so he is asking the question that you were talking about superlattices to Professor Sarkar. So his question is, can Fibonacci superlattices be a candidate or not?
It might be. Actually, people tried many different for instance, kind of binary, kind of ternary structure, and it is good idea to check. It is a nice question. I don't know. It might be interesting to calculate with this kind, but it is needed to consider a little bit large system size. But it's a good idea. It is possible to ask me via my email address and the other questions, since it is a short time interval and the number of participants might be high.
So if anybody still has any queries, you may please contact Professor Mehdi through email. Thank you, Professor Mehdi, for delivering excellent talk. We are really lucky enough to have you in this webinar series. Thank you, sir.
It was great pleasure for me, and hope to be safe everywhere. And I wish for all of you very nice day and time without COVID-19.
Thank you, sir. Now we are going to start our next talk. This talk will be delivered by Professor Rudra Shekhar Manna. Professor Rudra Shekhar Manna did his MSc in physics from IIT Bombay in 2006. He was a researcher at Pohang University of Science and Technology, Post-Tech, South Korea from 2006 to 2007. Then he joined Goethe University, Frankfurt, Germany for his PhD from 2007 to 2012, followed by a postdoc in the same university from 2012 to 2014. He did another postdoc from Augsburg University, Germany. He is a JSPS Fellow and also a member of American Physical Society. Currently, he is working in the Department of Physics, Indian Institute of Technology, Tirupati. His research interests includes phenomena occurring in strongly correlated systems, as for example spin-orbit coupled irradiation, triangular and Cagon spin liquid, valence bond solid, Mott metal insulator transition, Mott criticality, superconductivity, and magnetism by performing experiments at extreme conditions like very low temperatures, high magnetic fields, and high pressures. He is also interested in theoretical modeling issuing using first principles density functional theory for electronic band structure calculations. His quality of research is manifested through his publications in high impact journals like Nature Communication, Physical Review Letter, Physical Review B, etc. Today he is going to present the talk on low temperature physics with various exotic phases. Sir Rudra Shekhar Manna, sir, please.
Hello, good. Can you hear me? Am I audible?
Yes, sir. Yes, sir. You're fine.
Okay, good. So first of all, thank you very much for the introduction and for the invitation. And I'm also very much honored to present this webinar situation. And I hope everybody is safe and remains safe till COVID is gone. And so today, so I chose a topic which is the low temperature physics and the introduction also. Dean mentioned already, it's interesting, a different perspective, like different various phases appears. So I would concentrate there. And but I would go in a rather, more to a broad audience, because I suppose there are many MSc students or research scholars. So I would like to give what are the different topics, not rather concentrating one particular topic, and rather I'll give you various aspects why it is interesting. But if you have some question, of course, you can ask me at the end, to some particular end. And also I would like to also give some more, I'm especially mainly an experimentalist, so I would like to give some certain techniques which are also very useful, and students should know those such techniques are very much useful, and also give you some kind of overview. So I am now at the Institute of Technology, Indian Institute of Technology, Tirupati, which is the southern part of India. I think Tirupati, everybody knows where it is, at least in India. The temple is here. But so we are a new generation of IITs, the third generation. And so almost 5 years old, the IIT is third generation. And there are typical pictures I have shown you here at the my pointer. So here, this is the typical, all we are now in the current phase, we are growing up day by day. This is, we have about 550 acres of land here, and we started building. So this is already an old picture. Now there are many more buildings to come up in recent years. So now moving on to my slides. So this will be my my topics. So as you mentioned, the various phases, exotic phases. So that means I would like to talk about various phases. And starting with very simple, is what we know in everyday day-to-day life. But apart from that, there is also many things very interesting phases, very exotic, very unusual, at the same time very interesting. And that we need to tune. So like a temperature, or you can apply, if it's magnetic system, you can apply magnetic field, or maybe a pressure to the system, and so on. And then I will focus mostly two types of transition. One is mainly the superconducting transition, and what is the motivation, and why, what is the questions people are asking, and why it is interesting. And the second part, I will talk about various magnetic phases, where magnetic interactions, or the spins, magnetic spins, so to say, how they interact, how one can tune such phases. And in between, I will also talk various techniques, experimental techniques, how to deal, and what are the precautions one need to take, what are the informations one can extract, and so on and so forth. So as I mentioned, it won't be very much technical, but I would like to give overview But if you have certain questions, you can definitely ask me question at the end, or you can write me email, which is there in my website. So now starting with the phase transitions. So as you know, very often, very common example in our day-to-day life, which is the gas, liquid, and solid. Just take example of so water is an can have like drink every day, or you can or you can rents, like if you're in a colder part of the country, let's say, and you go to north, or you go in other countries, or you can just open your refrigerator, then you can see so that means or ice, so that means you can freezing, melting, whatever way there is a tune parameter. So here nothing but is a temperature. But also you can do also pressure, like you can think of in our day-to-day life, like we use in India, we use pressure cooker. So there basically we use pressure also, then it puts the melting points, the boiling point is drops, and then you can cook faster. So that means pressure also another parameter, which also it helps to tune the phases of metal. And when you talk about electron, the magnetic phases, then of course we see that magnetic field, how it is important, and so on. In nature also, it exists also in nature. So you can see this is the photo I took 2 years back in Iceland. So there you can see it's nature, how it's also beautiful. You can water, and you can this ice box, or there is also the glacier at the backside, and those the ice are, the coming and flow. The water, the phase. Of course, when there are different phases, then we need to talk about phase diagrams. So, and that typically tells you the temperature and pressure. So, x-axis is your temperature, and then y-axis is the pressure. And pressure has a different units. So, not to confuse, initially I define the pressure units. So, one is that the atmospheric pressure, ATM, and sometimes we call it also 1 bar, which is roughly equal to 1 bar, and which is also equal to 760 torrs, because pressure has different units. And now I give you an example, like in your football or in our bicycle of the bar, you can understand. I talk about bar or kilobar or Pascal, then you can already switch. You can already imagine how strong it is. Like temperature, if you boil at 100 degrees, so now you can go on room temperature, let's say 30 degree or 40 degree, 35. So, and then when you go to the the gaseous phase, we know 100 degrees. So we know how strong, or how, when you tell the low temperature, also next slide I will talk about, then also we discuss. In the water, thing is that the thing is of different phases. First of all, it is interesting, like one material you have, and you can tune to different phases. But the question is that so that is also one interesting thing. Why these phases are interesting in water, we know already. But there are certain lines you can see. There are certain lines which is the kind of, you can think of as a phase boundary. So which is between water and water vapor, or in ice. So these are also very interesting. What happens exactly at the phase boundary? So how the phase goes from one phase to another phase. So that we know from the lectures, or in colleges, or in the second order phase transition. So whether the two phases coexist, or then maybe a point which is called critical point, where all phases somehow coexist. So that means there is a certain point where one phases coexist, and there are also a lot of theories, a lot of experiments try to understand what is the nature, what is the criticality, or there may be a triple point where all phases coexist. There is a critical point, and of course it is interesting physics, and you can see, or this has to do some university class and all these things, and people have already got Nobel Prize in 1982 in this field. So now coming back to the temperature, because I will talk about mostly the temperature, main essential parameter. And then this when you temperature, but let us now have a look or how the temperature scales actually. So I think next of the slides talk about temperature in terms of kelvins. Is better, 0 degrees roughly equal to 170 Kelvin. And now, if you look at the temperature scale, so to get a feel of what are the different temperature limits and where we are at present room temperature. So 10 power 9, which is really hot, this is something, the temperature which you can feel at the, the center of the sun. But now where you come at the chemical energy of the order of 10 to the power 4, or the surface of the sun, just not the center, the surface, you can also of the order of 10 to the power 4 and all these things. Now, interesting temperature region where the origin of life at room temperature around 300 Kelvin. So this is in the Kelvin scale. And 300 Kelvin is of the order of again 27 Kelvin, 27 degrees centigrade also. Now, if you just even go lower, then you can liquefy the air also, which is of the order of 200 Kelvin or so. And then comes also the nitrogen, liquid nitrogen outside. We have like 77% of roughly 70 or 77% of liquid nitrogen in the air. So we can also compress it and we can get liquid nitrogen, and the temperature of the order of 77 Kelvin. And if you go further, then we need helium, which is outside is very scarce. So we need to have, if you do some experiment at low temperature, the liquid helium temperature is 4.2 Kelvin. And but it's very expensive because outside it's very rare. So normally when you do the experiment, you try to recover those helium, and then you can compress, you can reuse, recycle. Whereas nitrogen, it is not the case. That's why nitrogen is also cheaper. I think in a couple of slides I will give also some feel that how expensive those coolants are. And so the universe also we get on 3 Kelvin. Now if you go to even lower temperature, you can go to superfluid, where the next slide I will talk about superfluid a bit. And this is also of the order of 2.17 Kelvin. If you just this helium 3 and helium 4 is 1.17 Kelvin, where this also changes. Normal fluid goes to superfluid, where the viscosity goes exactly 0. But in condensed matter, what people try to do in this low temperature physics, they try to go as low as possible. But as you know that we cannot go to T equal to 0, and that violates the third law of thermodynamics. But we try to go at exactly extreme low temperature. So like people are doing laser cooling and all these things, where they try to go even nanokelvin range. So millikelvin, nanokelvin. The idea is that normally the atoms, they vibrate, and because of the thermal fluctuations, the vibration is a bit more, so you cannot control. But when the temperature is really low, so they're a bit slow down, then you can trap, and you can trap with the cooling and laser and all these things. Then you can trap, you can image, and you can study, different properties. So, but here I will. So in my talk, my definition is that the moment I say low temperature, that means below 300 Kelvin, it's a low temperature, and when it which is very low temperature, that is the nomenclature I will use, because otherwise if you outside is a bit cold, like less than 20 degree, you can also call it cold. But that is the definition I am beginning, I tell you. And now we'll see when I make a temperature dependence and all these things, then you can immediately follow what are the temperature scales I'm referring to or I'm talking about. And of course, when it's low temperature, then another important to be careful. If you try to do some experiment, of course, you have to somehow isolate your system, because otherwise, if you have a coupled system, then you cannot control the low temperature, because outside is whatever you can think of, and then so that you have to have devices. You can cryostat. So there may be some. I'll also show some pictures of the different cryostats, slides, and there one can really see how to isolate, so that decouple from outside, so that you can maintain the temperature and you can do different measurements. Okay, so moving on, that is helium. So earlier I showed the phase diagram of water. So now when the helium is, you're talking about helium, so it's beautiful outside. You have gas, it's very light gas, and I think most often there are all funny experiments students do. Normally, if you just inhale, then your voice is it's very weird and all these things. So, but if you make it pressure, you just pressure it, you can see Y scale I use as a megapascal. So that means Pascal is equivalent to roughly 10 bar, 100 bar. So that means you can have also have some kind of quantity. So now I'm wrong. 1 megapascal is 10 bar. So that means roughly 25 bar. If you apply 25 bar, now you can think of as a football, like if you have 4 or 5 bar, now you can scale yourself. Then you can also make it a helium gas kind of solid, or you can get a superfluid or you can gas. Superfluid, exactly the temperature, it's a very fascinating phase. If you can cool it down to very low temperature, like below 4 Kelvin, which is here the 4.2 is the liquid helium. And after that, at 2.17 Kelvin exactly, then it becomes superfluid. So that means if you are have a look in the glass crystal, where you can have a look at the liquid helium from outside, otherwise such a cold you cannot see, right? Then you can see the helium behaves like a kind of, you can see like a fountain. So that means no viscosity. Helium, these atoms, they can flow very wherever they want. It's like a free movement. There is no obstacle. And if you are let's say seeing this effect, then below 4.2 Kelvin you'll see helium is really like a very calm. It's like a or you can, there are certain experiments taken from American Physical Society website. Even that it was very popular, and people studied a lot across this transition what is happening. And there are also a model theoretically people propose is called two fluid model. So where people, so there's a normal fluid and then superfluid. So there are a lot of theory and experiments go the hand in hand. And subsequently also, I think 2 times Nobel Prize have been given in this field because of the very interesting phase. And of course, you can go to even solid. Helium gas also solid. This is also interesting. You can see the signature of such phases. Even sometimes they recognize it's a SCP phase, or you can get a BCC and you can go also SCP, the different phases also you can go. So coming back to the next phase, so that is superconducting phase, and that is at present it is very interesting phase people know, and I try to give certain examples of this superconductivity. And the name says that it's a conductor, but it's a superconductor. That means you can flow normally. Every day at home or house we have all these conductors. You can take it metals, which you have a lot of free electrons, so they can carry your electricity. But if you can think, there are good conductors, normally copper, silver, or gold, aluminium. You can think of this one. But at certain point, it gets superconductor. So let us try to understand what is superconductor. So everybody knows, I think from our school days, we know what is Ohm's law. So Ohm's law is nothing but V equal to IR. So that means you have a sample, and then you give some current or voltage or other way around, then you get resistance. And that is how we measure. Normally, there are also different techniques how we measure. You can measure 2 probe or 4 probe. That is also a standard experiment, which we I think all students we have done BSc or MSc. The advantage for a small sample, we use the resistance, we use the 4 probe, because we need to take into account the contact resistance, because you apply the current at the both sides of the sample and you measure the voltage in between. So that means the contacts are not same. In case of 2 probe, you use the same thing. That means you take into account all this contact resistance. And the moment you are measuring very low, resistance sample, then you can get a lot of error bar. Now the question is that then that means you send some current here, and the microscopic mechanism is very important here. So that means you send some current, and then there are, as I mentioned, a lot of metals, there are a lot of free carriers like electrons, and what they do, they take the current and then move through the sample one side to the another side. And while going through this side, then you have a lot of barriers and some obstacles which you follow, that is which you measure as a resistance or the voltage drop. That's why you call it the potential difference. So you take a potential at one point, and the potential is changing because the electron is carrying the current. Because of this lot of obstacles in between, then they lose their energy, so to say, and then you can come with the potential at different point, and then you measure the potential difference. That is nothing but resistance. And then how strong? If you take an insulator, for example, the resistance is more. That means, or maybe huge, so that you cannot. Let's say they cannot. That's why you send some current, then you cannot. Now that you can also think of another real-time example, like you are running in highway in the very early in the morning, less crowded, less traffic, or you are driving a car, and then you can see you can drive very fast. But as you know, in the office hour or something, there are many people on the road, and then you have problem because you have to find a route or there are a lot of traffic jams and all these things. So a lot of obstacles. So you can think of also in that direction. So that means resistance very important. But now the question is that, so of course in real time, all these materials as you talk about, all this copper or they have certain resistance, although they're good conductors, but they have certain resistance. So the question is that by some means, whether we can reduce the resistance and make it completely zero, so that whatever the current which you are you're supplying the sample goes freely from one end to the other end without having any resistance in between. So that's called called superconductor. And another important aspect is that if normally we know the power dissipation is P normally I times current times voltage, and you can write also I square R or V square by R. Now the thing is that if you apply some current to the system, there is no dissipation. And that means if the R goes to zero, the resistance of the material, then there is no power dissipation. And so that is a very big to the society, because each and every month what we pay the electricity bill, so that is nothing but our the power dissipation called in terms of watt hours. So, but in case there is no dissipation, then like you have to give power at the current at the beginning something, and then it stays there forever. So we don't need to pay any electricity bill. Now, so this is another advantage, why these materials or the superconductor are important. And that is real sample, those who are interested in experiments, that you can see how the contacts are done. Then how the contacts are made. These 4 contacts I just talked about, current leads and voltage leads, how they're made nicely. And there can be a different, mechanism how you make contacts. There are silver paste, carbon paste, or you can very hard sample, you can do bonding and all these things. And different sources also, how they how the mechanism, so the resistance, how they are the microscopic origin, basically when the electrons carry the from one side to the other side, so that means they can hit each other. They can also hit with phonons, that lattice vibration, that is nothing but phonon, but previous speakers talked about very much about the phonons. Or then maybe some defects, and then maybe some, if it's a magnetic system, there can be magnetic impurities. So there are different scattering events. When they hit when there are more number of scattering process, more obstacles, then more resistance. It's like that. So now this is the first experiment was done in the Netherlands by this Dutch scientist group, and actually the initial experiments was done by the students, and when they were doing the experiment, they suddenly saw they are doing mercury. Then suddenly saw the resistance drops exactly at 4.2 Kelvin, drops to zero. Initially, they didn't believe, so they thought maybe sometimes when you do experiment, then you may think, okay, that is an experimental artifact, or that may happen. There may be some electronics problem and all these things. But then they repeated. They asked you, please repeat the experiment when you do certain experiment. Then you repeat the experiment, and each and every time they found that they are dropping the temperature zero. Actually, that time they were interested not about superconductivity. That time they were interested how to go to even lower temperature. Basically, they were interested in the liquid helium, because exactly at the 4.2 Kelvin where helium gets liquid, but that was kind of add-on. And then they try to understand, okay, resistance is zero. That is really peculiar thing. And later on, they found actually it is the case. And that is simply mercury. So that they take simply one element, a single element. They try to understand what is happening. And there are, in this field, there are a lot of Nobel Prizes given, I think, to understand the experiment point of one aspect. Another thing is that it's a diamagnet. So diamagnet, what is diamagnet? So that means it is kind of if you apply magnetic field to the system, and one can define in terms of magnetic susceptibility. So that means magnetic susceptibility is defined by and that is nothing but also the order parameter. So at the beginning I forgot to tell you, so every phase transitions are happens to, there should be an order parameter, that means which the parameter, the microscopic parameter which leads the ordering of the material. You can think of as a density, how the density of the changes, that means the distance between the molecule, how this changes, order parameter. And for magnet, it is the magnetization. The definition of order parameter was given by famous Russian scientist Lev Landau. And for diamagnet, it is exactly -1 or negative, and for perfect diamagnet, it is -1. So that means if we apply magnetic field, so that means the magnetization or the magnetic field lines, they are somehow expels, so that you can see. So initially you have below TC, so that means you should be in the superconducting state. Then you apply magnetic field, and somehow your material is in the superconducting state. It expels whatever fields were inside very much outside. And if you do the magnetization, this is the curve which you measure. This is also measured with the lead. Lead is also superconductor, which is superconducting TC of 7.2 Kelvin. So then you can see suddenly there is a jump, and that is a -1 exactly. That is called a perfect diamagnet. That means you otherwise every materials normally has a weak diamagnet, which is negative, but not exactly -1, and that is the very peculiar example. And that can be also, it can be seen, this is called Meissner Effect from a popular German scientist called Meissner. And based on his name also, there is an institute near to Munich, Germany. It's called Walter Meissner Institute. And what you can see, there is a superconductor, the black material here. So, and the bottom you have a magnetic field, and you cool it, cool with liquid nitrogen, because it is a different material. It's called high TC superconductor, yttrium barium copper oxide, which has a TC above nitrogen temperature. So that's why I left 90 Kelvin. And then you can see if you just cool it down and then you put the material, it is kind of a floating. So this is the perfect diamagnet. That means it expels every field outside, and as if you can see this levitating or it is floating. And that is a huge applications. Like you can think of as a train. People are thinking there is also a lot of demonstration. And a small scale, if you can create a track with a lot of small magnets, and on the top you can put your samples with superconductor, or your train is made up of, let's say, superconductor. That means you can just initially supply the energy to the train, and then you give a small push, then it is levitating. Of course, you have to think of in terms of the air resistance and all these things. And if you can somehow overcome all these things, then the train goes up, forever, or at least to some extent, and then we don't lose any energy. So because nowadays we are talking about a lot of energy point of view, how to create a lot of energies and all these things, then these things will be solved. But the main problem of this all this scenario is that always you see at low temperature. So that means the temperature is really a barrier. And now I will talk about also what are the other obstacles in this area. And so here I will talk about in superconductor also. As I mentioned, I don't go to very details. So there are also certain reasons why also get a Nobel Prize here in this BCS theory, call it Barton, Cooper, and Shekhar. They come with a theory around 1980s. That time they got a Nobel Prize. And the theory tells, so that means we are talking about zero resistance, but how to understand that zero resistance? So that means, and we understood the microscopic mechanism is that this the scattering event or scattering mechanism. So is there a way to reduce those scattering mechanisms so that there is no loss in energy, so to say? And they came up with a theory. They call it Cooper pairs. Somehow the electrons, these two electrons, you can see they make a pair. But the question comes to everybody knows electron is a negatively charged particle, but how they can make a pair? They cannot, because of the strong Coulomb repulsion, they will repel each other. But the thing is that they come up with a theory, which is, they call it, we have lattice, that means phonon, and like the positive ion cores here. And somehow when one electron comes to the phonon interact, that is called electron-phonon coupling, and somehow together they create kind of a positive environment. And with that positive environment, another electron comes and it sees the positive environment, and then together they make a pair. So that means the electron, they make pair, that is called Cooper pairs, and via phonon. So you have the positive source, because you have to have a positive source, otherwise they cannot make pair because they hate each other because they are negatively charged. So that's why the total thing, so it's a virtual process. So that means that they are not in a material, they are not stopping electron, they are always very much delocalized in this case. Then, so that's a virtual process. So one electron interacts with this positive environment, and then together they are moved. So that's why there is always a gap. So there is always a gap, like of the order of angstrom level, but still they are kind of form kind of a bond everywhere. So now in a material, if you can think of everywhere, some such bonds are, such pairs are happening, which they like each other, they don't collide with each other, they don't scatter, and that's why they don't, have any source of the scattering mechanism, and they don't lose any energy. So that's why the resistance is zero or very close to zero, which is very negligible. And when electrons became a pair, that is called also Cooper pair, and they are boson because they are not electron anymore. And is there some question? No, I suppose. So, okay, good, thank you. And so that means the boson, that means one has to deal with the Bose-Einstein statistics, because earlier it was fermion. When you treat the one electron, single electron, that is a fermion. Then, but when you talk about the boson, this is Bose-Einstein condensation. One has to also treat the statistics in that way. And there are different types of superconductor, and there is also a model. It's called two-fluid model, also applicable here because it's a normal conductor. And then if you come to the superconductor, it's called superconductor. And here the phase, earlier I was talking about the temperature phase, here temperature and pressure, and here temperature and magnetic field. And now you can see, if you apply the magnetic field, of course, if you coming the x-axis only temperature at below some Tc, you get a superconductor here. But the question is that whether this property always remains same, but it is not the case. If you have a magnetic field certain level, so that I can go back to the previous slide, you can see if the magnetic field is also very high, that is called critical field. So below Tc, then also it is, you destroy the superconductivity. So there are two parameters. One is the temperature. Of course, temperature should be below the Tc. And here the magnetic field also below the Bc, so the critical field. So that is exactly the phase diagram it is showing. So below Bc, so that means this is the temperature and field, that region you are superconductor. That is some kind of limitation. And you have above it is a normal conductor. So that's why that is also different phases by means of these two parameters. And if you're type 2 superconductor, that is the more different. And they talk about this electron pairing, how this pairing happens, and there are different mechanisms. And there are different phases. So that is a superconductor, which is very much similar to the type 1 superconductor. But type 2 superconductor, there is some theories there that is called a mixed phase. So that means you have a normal conductor and superconductor. So that means when you appear to this BC1, you don't destroy the superconductivity fully, rather partially. But when it's BC2, then you suppress the superconductivity. And in between, you have some kind of state, which is also called vortex state, and which is some mixer of the state. And but in this case, the Tc is somehow people found a bit higher or above nitrogen temperature. That's why these type 2 superconductors are normally people talk as a, in the literature it is called a high Tc superconductor. And the name high Tc, the name is a bit misleading. That why they call it high Tc, because the Tc is above nitrogen temperature, because nitrogen is very much cheaper. So in that way, people can think of the temperature somehow enhanced. And not only that, when people are measuring the if one goes to the history of superconductivity, because 100 years old topic, and initially they were founding the Tc, they're stuck around 30 Kelvin or so, but suddenly there was a jump from 30 to above nitrogen temperature. So in that way, that is really high with respect to the type 1 type. So but in order to distinguish type 1 and type 2, one has to do the magnetic field measurement, and then to understand what is happening whether it's type 2. But if you measure temperature wise, that you don't get any clue whether it's type 1 or type 2. So simply type 1 superconductor or type 2 temperature doesn't tell you that what kind of superconductor it is. And I will give you also some more examples where one can see also this feature. The temperature is very high, but it's also type 1. Okay, so now coming back to this one, how one can measure also. Then once you have superconductor, then one can play a bit. There are different things. This is called Josephson junction. So that means you have two superconductor, and in between you have also insulator. And then insulator means or some isolator. So people try to understand how to tune, so that you can see in between there is a kind of a barrier. And normally, which in case instead of if you don't have a superconductor, you take normal metal also. If you can have this kind of junction as a metal, like you have metal, and sometimes electron can also tunnel, which you cannot explain classically because the potential barrier is too high. But if you explain quantum mechanically, then the phase somehow, the wave function somehow can go, or this is the term which we measure the tunneling mechanism. But instead, if you don't take the metal, you take superconductor here. So here the tunneling mechanism is that there is also tunnel happens, but instead of electron, the Cooper pairs they tunnel from the barrier. Even though there is a barrier, of course, that is called a weak link. So if the barrier is very big, of course, you cannot tunnel because that has some kind of energy. It has to win. But these are all electron phonon pairing, and the Cooper pair they can tunnel from one side to the another side. And now there is one technique, and what is the use of this one? Because nowadays people measure all these magnetic measurement with a very sensitive probe, which is called a Squid Magnet. And what they do, basically, they simply the mechanism is that, so that is one junction. So that one here is one junction. There they use two junctions. That means they call it Josephson junction. It's very simple. This side is superconductor. In between this, these gray regions are kind of the isolators or the insulators. And once then they have the tunneling, and what is the advantage? Then you apply magnetic field. So there are two Josephson junctions, and you apply magnetic field. Then of course the flux changes. If you put some magnetic sample here, and the sample normally inside. So if it's a magnetic sample, if you apply magnetic field, then the flux changes. And that flux you can measure really in the flux quantization. You can also calculate here this equation, the flux quantum 50h over the Planck constant by 2e, and 2e is nothing but this Cooper pair because 2 electrons, and that's why 2e. And then this flux you can measure really precisely, very much very sensitive technique. And also because the magnetization you can measure also simply electromagnet, that is also different. Like you have a sample, and then you can vibrating sample magnetometer, you put a magnetic field, you change your sample, but there the sensitivity is not that high. So that's the principle they use the Squid magnetometer. You can measure also 10 power minus 7 or minus 8 EMU electromagnetic. And how they do a typical magnetometer, which is commercially available, you can the principle inside. So this is also a cryostat. Outside it is isolated, and it's a magnetic system. I think one demo picture is given. Like if you have a ferromagnet, you can see the hysteresis, how the hysteresis is measured. And that is quantum design. The company they sell this one very high-end equipments, and you can measure that precisely measurement. And inside the device, you can have magnetic field of the order of I think 5 to 7 Tesla, or you can go to lower temperature as low as you can. Like if there is some provision, you can go with millikelvin temperature range. And then how it is measured. So you can say, I show you the kind of typical diagram. So this is the Squid, as I mentioned. The total name of Squid or the full form is Superconducting Quantum Interference Device. So what is called quantum interference, one can think of it as similar to like we can optics. We have to double slit experiment, and then we can also interference happens. Here also the similar thing happens in terms of flux quantization, and that's called quantum interference device. So here you have some coils, and what you can see, the sample is normally move through this tube which I mentioned here. This black one is the blue one is the sample, magnetic sample naturally, and then it's moving through the coil. And then how the flux changes, that you can measure in terms of voltage. On the right hand side, you can see when the sample is moving through this one, and you see a signal. And it is very Okay, I think it's a background noise. So I think so that means the sample has to be kept also inside the magnetic field in order to have the the total magnetic field how we can respond. The field normally at the center of the magnetic field is very high, not only high, also it is more homogeneous. So those things one has to take into account. So that is the typical measurements one takes. So you have to put the sample and put it inside, and then you some kind of a variation within the magnetic field, and you get a signal. Then you try to analyze your stuff. Okay, so then now one can go even how we do like as I mentioned, if you have certain sample which you have very much pressure sensitive, like you take lead. So lead is also I have shown earlier measurement also you have this is the magnetization or the magnetic moment, and then you can calculate magnetization or the susceptibility easily. You just divide by the magnetic field, and then this is the room temperature. Sorry, the ambient pressure, zero pressure, the phase transition at the late 7.2 Kelvin. But if you apply pressure to the system also, then your superconductive transition, you see it is even reduces to the lower temperature. It's roughly 2 gigapascal. So 2 gigapascal of the order of 10 kilobar. So now you can think yourself how strong the pressure is. So that means, and then means you can put everything in your sample inside a pressure cell, and then you can it depends what kind of sample you are interested in this case the lead, or you can have some other samples which is really pressure sensitive. Then how the magnetic interaction, all these things changes, then you can also tune, and the whole thing can be placed inside a this Squid magnetometer, and then you can also measure. Of course, in when you apply pressure, then of course there should be some pressure medium, and you can use gas or liquid or solid also, because the people use in order to go very high pressure, like if you use helium people use also gas pressure. But then the problem is that helium is highly compressible. You cannot go to very high pressure. But you can use, in this case, the Daphne oil. There is a Japanese oil used as a medium. Or sometimes people use also when you use anvil, diamond anvil, and all these things. In this, these are called anvils. They use even solid medium. So there you can go to even high pressure like 100 GPa and all this things. Very high pressure, very dangerous in fact at the same time. So one has to be very much careful. And for magnetic measurements, you have to be also careful. Like these things also gives you the background, because your sample is sitting just at the center here, but you have whole pressure cell is inside. I mean, you are also measuring the whole pressure cell. So you have to choose the material of the pressure cell such that so the pressure cell you make such a way that so that your background noise is also very much less, so that otherwise you don't get your signal from your sample. But if your sample is very high, your sample has a huge signal, then you all forget all these issues. So, and this is the typical, the setup looks like for a bigger cryostat. That is another cryostat, which I think is the magnet you can see sitting. You don't need to think here. And this is the pressure cell which inside, which I will show even some more pictures at the end to get you some feeling. Or I think those who are doing experiments, I think the students' point of view, I think they should realize the experiment is not like it's a black box. You go and do your measurement. Rather, you design something. You see how the measurement runs. What is the difficulties? What is the am I audible?
Yes, sir. Yes, sir.
Good. So and that is also this kind of magnets, the super kind of magnets, superconducting magnets they use in the Large Hadron Collider in CERN. So and the magnets also, they are now making all the superconducting magnets. So the TC of the order of 1230 Kelvin, and in this Large Hadron Collider in Switzerland. So that's the three countries: Switzerland, France, and Italy. They have, I think, a huge 20-30 kilometers long, because they want to track the the particle inside the magnetic field, and they use all the magnets in superconducting magnet, because they have to cool with the liquid helium. That means you are pretty much in the your energy is not very much required. Initially you apply those things to the magnet, then it remains like that. So there are various examples. And although other application is that people use in this MRI machine, we take some image if you have some, if some break your leg or whatever, then some tissues or ligaments, or you do this MRI. They use also the superconducting magnet of the field of the order of 5 Tesla or something like that they use. And this is another example which I was telling I think a couple of slides before. In Germany there is one lab, so which also they demonstrate. I think it can be also. You have a track made of magnets, or maybe you can put it other way around. You can put some magnets which are having, let's say, a couple of Tesla, and then you can put some superconducting magnet which is TC should be low, so then it is floating. Then you can think of kind of transport system. So then just you give a push, then it just follows. If you make a circular path, then it goes across this line. So that's why it is very much interesting in different perspective, not only power point of view, also the energy point of view, both aspect in our day-to-day electricity point of view, also in terms of transport mechanism. So once it discovered, in temperature, then it will be a revolution to the society. And there's certain also risky to the superconducting magnet, because there is called magnet quench. So what happens if you have superconducting magnet? So there is a power, as I mentioned, R equal to 0. So that means power is almost dissipation 0. But if you have if the magnet is somehow in the superconducting state, but it somehow there is some disturbance, or somebody gives some push to the magnet, so that means a lot of energy is stored inside the material, the magnetic material. So that means when the superconductivity lost, or if your magnetic field is high enough so that you kill the superconductivity, then whatever power it inside, then it all will release all of a sudden. And that's why you can see helium is there's an accident actually. It is not good to see. It is good to see, but not the person who is doing the experiment. There are a lot of, it's risky, and a lot of pressure will immediately jump in, and all rooms will be quiet. So that is another, this is called superconducting, the magnet quench. So that means the lot of energy is there, immediately released, can be also risky. And now over the years, people are also, the goal is that to drive the things to the room temperature, and then you can see the temperature and the pressure, the year wise, how the evolvement. So initially, as I mentioned, mercury started or the lead, and then they started with two metals together, like Nb3, tin, or germanium, and all these things. But TC was very low. And here around 83 or 84, or at this range, they found this material, and suddenly the TC raised. That's why you call high TC. And you are in the room the nitrogen temperature here. So after that, people started mixing also. They don't understand the mechanism, because type 1 superconductor, they understand that it is the electron form mechanism and the BCS type. But here at the room, here in this question, there are a lot of theories. People still don't know what is the exact mechanism of the electron form mechanism. So that's why somehow stuck 150 Kelvin, so which is still of the order of minus 200 degree or minus 100 degree centigrade. And very recently, there is also hydrogen sulfide. You take a gas, then it is also, you can you can make it solid with very high pressure. And this is also, they got also lanthanum, this hydrogen 10, and this also you get 250 Kelvin, very close to room temperature, but very high condition, extreme, because that you cannot use in practical purpose. But because the pressure is also very high, I think of the order of 2, very high. But people are trying to get, at least if you can reach the room temperature, or somehow in the chemical point of view, whether you can tune so that you can use the room temperature. So, but the main question here is that, so as I mentioned, so the mechanism is still missing. So that's why people don't know. But sometimes by luck, maybe, or by chance, people are getting some sort of the different superconductors with that room temperature, or close to that, but still is yet to find. And the price point of view, as I mentioned here, you can see there are different prices also. Like you can have the liquid helium of the order of 10 euro per cost. In Indian money, you can convert very much. The liquid nitrogen is very cheap. And if you go to liquid helium 3, which is even much higher, which is beyond imagination. But people are doing all such kind of experiments when you are going to really very low temperature. So now I switch to another, this magnetic transitions. I would be rather short because I'm running out of time. So magnetic phases, the moment you talk about the magnetic phases, so that means the first thing comes to our mind is the quantum spin. So which is the electron spin, which is, you know, classically, which you cannot explain. One is to have quantum mechanics, because classically you can think of like, you know, you spin something, but if I ask you, you explain certain things in terms of a point object, like you or the electron, so that you cannot describe in terms of, you know, classically. So then one has to do the you know, the quantum mechanics, and that's why the moment you talk about magnetic phases, so the new definition came in the quantum mechanics, and this is nothing but a spin angular momentum, and this started with also the famous of different how the electrons spin. They discovered initially, they measure the orbital angular momentum, then they know how the electron spin angular momentum, how it is taken into account. And normally the magnetic systems, when we talk about the partially d and f shell orbitals, mainly the transition metals or the heavy fermion, also the f shell electron also, because there you can do, when it is a fully you know, filled state, then of course there is no conduction, because it's completely shelled orbitals. So, and now you can think of how we can feel. So that means in a system there is lattices. So, or this can be also different types. Here I showed as a square lattice, because square, and you can have also triangular lattice, you can have also carbonyl lattice, you can have also hexagonal or honeycomb type. So to give illustrated that, now you can feel the electrons, the spins here. So when the spins are here like aligned, you know, all parallel, then you call it ferromagnet. And now if you parallel one up, one down, next up and down, then it's called antiferromagnet. This is very simple thing, very easy to, but there can be also very complex, that I will also show later on. And because ferromagnetic system, people know for iron, for example, which was very much popular earlier days, and people know also that people used to think that that is very common magnet, but apparently nowadays whatever magnets which you find is mostly antiferromagnet, and it is very much complex, and not only complex, it's very much also interesting, that I will talk about it in some slides. And for this one, you can, as I mentioned, for unpaired electrons, you know how the magnetism, you just apply magnetic field, then you calculate the ability, which is nothing but 1 over T types of dependence. Or and if you have the electrons, they are interacting each other, and they have some kind of a interaction between the adjacent spins, then you develop the Curie law device into Curie-Weiss law. And then one can also see the typical examples of the magnetic susceptibility for different phases. So here the magnetic phases are paramagnet, ferromagnet, or antiferromagnet. So paramagnet, you know, it is simply 1 over T types of transition or the behavior. And that can be easily seen in the this right-hand side plot, because if you plot 1 over chi, that is a chi inverse, that means you get a simply linear as a function of temperature. But in case of a ferromagnet or antiferromagnet, then you have to take into account the interactions. So after some point of the temperature, then they try to, because of the thermal fluctuation, you don't see any order. But if you cool it down, then you see the, in ferromagnet, you call it Curie temperature, and in antiferromagnet, you call it the nil temperature. And that is how you define in terms of Curie-Weiss temperature in this plot. This is very easy to visualize. So that you can see the Curie temperature, Curie-Weiss temperature is positive for a ferromagnet and antiferromagnet. So that means you do a measurement for a sample, then you know what type of, you know, magnet you are dealing with. And there are typical examples, you know, ferromagnet and antiferromagnet, Tc and Tn is the antiferromagnet for different substances, chromium, manganese, iron, cobalt, and nickel. And so these are for elementary magnets. So now we go to a little bit more, detail of this one, which is not a very standard magnet, but the different magnet, which is called a frustrated magnet. Now I draw a lattice in the triangular lattice, where I choose the ground state as antiferromagnet. So that means one spin up, one spin down. But now you see, if I put a spin at this position, if I put up here, then this is fine, this antiferromagnet, but this interaction is violated because it's ferromagnet. And if you put down here, then this interaction is antiferromagnet is fine, but that is ferromagnet. It's problem. But I told the ground state should be antiferromagnet. So if you take a sample also, this you always get the Curie-Weiss temperature is minus negative. That means antiferromagnet. But in a system of having this kind of triangular lattice, then that means you can have this kind of different degeneracies. So that means if you put here, or you can do two types of system with the same energy, you can have also here, and you can have also here. So that means this position or that position system doesn't know what to do. The spins is somehow call it frustrated. So that means that is our definition of the frustration. It's called geometrical frustration. There are another type of frustration also involved. And when these kind of are appearing, so the spin somehow behaves like a phase. It's called spin liquid, which I won't go very details here, as I mentioned. So one can think of this is a paper front page, cover page paper from some Nature paper from Oxford I have taken. And there also we have, you see the spins are somehow kind of different, one up and down. Although we are measuring a solid material because it's condensed matter, solid material, but the spins are somehow behave kind of liquid, some kind of you can think of kind of a disorder phase because system doesn't know what should be the real ground state. And that kind of things will gives you a kind of a spin liquid phase. And so normally what you expect and what is the signature? So that means the moment you have antiferromagnet, that means you have strong correlation between the spins. But if you then you expect you cool down the temperature, then at some point you get a phase transition, the antiferromagnetic order. But in this case, what happens if you, because of this frustration, system doesn't know, then system, if you go to very low temperature, but system doesn't order, or in case it order it very much low compared to the Curie-Weiss temperature. So that is the Curie-Weiss temperature, and then it's low. So you can think the frustration is more, then there is no magnetic order in the system. That means the parameter goes infinite. So if you put a Tn0 or there is no transition, that means try to understand if there is spins are strongly coupled, they interacting, but you don't see any order of the system. But they are somehow kind of correlated because of this that is called quantum entanglement. So they are somehow or overlapped quantum entanglement. They have information from one side to other side, but because of this frustration, they cannot order. So that is called a quantum spin liquid, and it has a very much application to the quantum computing. And at present days, it is very much interesting topic how one can replace with classical computing with the quantum computing. So there are different other signatures how one can detect this. This is one signature, but there are many more which I am not going into details. And to go to I will show a couple of other phases where the spins can orient in a very very fascinating or very exotic fashion. And so that you can see this particular phase in the phase diagram. This is also a material which is called MnSi, and where the manganese silicide, where you have magnetic field and the temperature. And here what happens in this red zone, so there are other phases appears like the spins can have kind of conical, kind of helical structures. Here in the helical, here in this phase you have a conical phase here. But this particular block here in the red marked here, so spins are some kind of very unusual phenomena or the structure, which you can see. You can kind of a topology outside here, kind of restricted boundary, and inside you have a very different structure. Sometimes you can have this kind of structure, sometimes you can have this kind of structure. And it seems all spins are somehow falling, at the center, and here it is a bit off center. And if you look at the 3D phase, it looks like the 2D and looks like a kind of you have information or communication between these lines here from up and down, up and down. And this particular phase also nowadays very interesting. It is called a harmonic phase. And people are trying to also get room temperature, and already there are different groups, like groups in Japan, in Tokura, they already achieved room temperature. Now they are thinking how to go to in the company point of view or industry point of view, because they can lot of store data, and you need very less power, because when you talk about spintronic device where you have the hard disk and all these things, the power which you require here in this case you can require very less power, much less, and you can store a huge data. So that's why in the technology point of view also very much interesting. And so now there is another type of magnet where this is also a honeycomb. So instead of a triangular lattice, you can put also hexagon. I mean, honeycomb. There are also spin structures. It is not in plane. All these shaded marks are the spins are going out of plane. So in that case, it can have also like zigzag. So that means one plane is ferromagnet and the next line is antiferromagnet. So this line and this line, the spins are in positive direction. I mean, one direction, that is anti-parallel basically. Sometimes you can have out of plane. So there are different types of plays. Now it pretty much depends on what kind of things people are interested in, and then you can study different magnets, different structures, and there are different way to calculate. Also theoretically, also you can calculate how the interactions are there, and what is the dominant interactions called, say in this case, the two neighboring speeds. And now I talk about a little bit of the experiment and the two experimental tools I will talk about, then I will finish my talk. So one is that high resolution delatometry, which is a pretty unusual technique. And one is that, we know thermal expansion. When we know there is a gap, is called fish plate. So because of the thermal expansion, that you need to have a gap so that when the train comes, because of the heating, it can compensate the extra resistance. But now the different things. So how one can measure such? In a bulk scale, you can measure. You take a scale, you can measure the length, and you can measure T. Then you can also measure what is the delta T and corresponding delta length, how it's changing. We measure a different technique because we are measuring in a very small. So that means you have a parallel plate capacitor. You can put a sample here. So that means when you change the sample dimension, then the capacitor plate changes here, and then you can measure the capacitance. And then indirectly you can measure thermal expansion coefficient, and then you can measure also different thermodynamically. Also you can see. And so I don't go to very details here. So I just keep there, and then you can see a typical single crystals, how you can measure the samples in different direction, how it is expanding and contracting. And that is also a typical measurement setup. The dimension, how it's changing, and you can also use a commercial equipment. You can put every setup inside the things, and you can different techniques, lot of thermodynamics. These things can be also done in very pressure dependence, because as I mentioned, the lattice, if you want to apply pressure, then means the lattice also squeeze, and then that is the wavy pattern on the background. And then also it can also have some effect in the phonon background, and that also you can study. So I can skip these measurements, and there is also another type of measurements, this heat capacity. That is also you can do very sophisticated measurements, that you can measure heat capacity. You can measure a heat pulse to the system, how the temperature is nothing but heat capacity. But that can be also thermodynamic measurements, and then you can see the sample is put it inside. Your heat should not be dissipate, so you have to be very much careful. And then how the temperature changes in the material. Then you can see how these 9L wire are connected, and the sample is somehow hanging here. And then you can measure also heat capacity. And from there also from heat capacity, you can also calculate the electron phonon background, or you can have electronic properties, or if you have some magnetic system, you can have. Okay, so I like to. There are many other techniques. I don't want to go into details here. Already have a couple of systems. I just focused here so that you get a feel that different measurements are done, and how the different physics extract.
I guess there is some internet issues. Sir, you are not audible now.
Hello, Professor Manna. Sir, you are not audible.
Hello.
Hello.
Hello. Sir, you are not audible.
Now?
Now it is okay, sir.
So is there some question?
Thank you, sir, for this wonderful and lucid presentation. Now the session is open for discussion. You may please raise your hands, those who want to ask questions. Any queries? You can put it in the chat box also.
Someone from SIMP, can you please read it out?
Sir,
In the chat box.
hello, sir.
I cannot see the chat box for some reason because I cannot because in the full screen.
I will read it out, sir. I will read it out.
Yeah. Ah, no, I can get it. I can get the question here. Right. So the question is, I just want to know what kind of measurements you have done in your lab. I mean to say what specializations in your lab. So what we are trying to do, actually, we are trying to do the pressure experiments and together with magnetization, resistivity, and at the same time we are also doing the thermal expansion, and so we are developing the systems, and so that is what we are doing basically. So thermodynamic measurements mainly, but transport and also the pressure studies that we are planning to do. So not yet done, but some things are already arrived, so we plan to do in that direction. So that's all. Any other question?
Any other questions? So there are some questions from the YouTube also, so I can read it out
Please.
to you.
Yeah, please. Thank you.
So the first one is what are the parameters to determine whether the superconductor is type 1 or type 2? Somebody has asked a question.
Yeah, very good. So maybe I was a bit fast there. So normally type 1 and type 2, you have to apply magnetic field to the system. And if if you can suppress the superconductor just by applying one critical field, then you can see it's a type 1. So that means all field lines goes through the material, that is type 1. But in case of type 2, then you have to have this mixed phase, the vortex phase. So that means initially the BC1, the magnetic field starts to penetrate the material, but still you have the mixing of two states, the normal state and the superconducting state. The moment you go to the superconducting state, the BC2, then you suppress the superconductivity completely. So that means the magnetic susceptibility is the important tool to determine whether it is type 1 and type 2.
Sir, there is another question from Lakshmi J. Hatia. The question is why we take low temperature magnetization value to calculate Bohr magnetron for cation distribution. Sir.
Okay,
Sir, am
so
I audible?
yes, you are audible. I'm trying to understand in which perspective. I mean, low temperature. I mean, what my point is that, I mean, I didn't understand your question fully. But Ajay, why is the low temperature value?
Hello, sir. Hello, sir. I am unmuting her. Hello, sir. I am unmuting her. Actually, he has also raised her hand.
Okay.
Hello, Lakshmi. Hello, Lakshmi. Hello, Lakshmi. Hello, Lakshmi. You can ask the question directly.
Hello, am I audible?
Yes. You can go.
Low.
Sir, generally we are doing cation distribution using low temperature magnetization data. So my question is why we are taking low temperature magnetization data other than room temperature data?
Correct. I understand your question. So the thing is that, so the low temperature, the important point is that, of course, if you take a magnet, normally when you do magnetizing, that means we are talking about magnetic samples. Yeah. But sometimes what it happens, if you have some feature, like if you have a phase transition at room temperature or higher temperature, doesn't matter, then you do it. So magnetization is nothing but you just, you have a magnet in sample, you just apply magnetic field to the system, and then how the magnetization changes how the magnetization is susceptible to your magnetic field. But there are certain systems, or the system which I showed mainly in my presentation. There, what happens because of the thermal fluctuation, and although the spins, they're talking about the spins, they have a nice correlation, but the thermal fluctuation is so much, the energy scales point of view, you don't see the magnetic energy scales. So the moment you suppress or reduce the temperature, that means you are suppressing one energy scale, and that means your magnetic energy scale, they try to show their effect. So that's why you have to do. So that's why in a system you have to know the magnetic energy, how much magnetic energy, how much magnetic field you need to observe such effect. That's why that is the definition, nothing else. So the temperature, the variation is, that is the way people see, if you know the how the magnetic energy scales.
Okay, another
Thank you,
question.
sir. There is a
I have one more question related to
Okay.
can we take room temperature data for the same?
Yeah, sure. So that's why when you start the measurement, you take the room temperature data. But then it is your magnetization. Magnetization you can measure at any temperature. Magnetization is initially nothing to do with the temperature, because you are, as I mentioned, you have a magnetic sample. You change your magnetic field, then you see how your magnetization is changing. But if you have some, some interesting phase, or if you want to study the magnetic correlation, the magnetic phases, may be very much interested in the low temperature, because the magnetic energy scale is much lower compared to a thermal energy scale. At that time, you have to go to the low temperature. That's why you do the temperature variation. Like if you measure the magnetic measurements, you start with the room temperature data, then you keep on measuring at low temperature. Then you try to see whether some exotic phases is appearing or something is changing on.
Okay, thank you, sir.
Thank you.
Soham asked your question. Hello, Soham. Hello, Soham. Hello, Soham. Hello, Soham.
I can read his question, I guess, in the chat box. Ferrimagnets such as layer ferrimagnets may lead to very low temperature. Can it be a good candidate for ferromagnetic magnetic cooling? Okay, magnetic cooling, it is a different thing. So it depends. Again, all depends on the different things. So it depends on how the magnetic interactions are there. So magnetic coolings, the moment you talk about magnetocaloric effect, basically. So as you change the magnetic field, your temperature drops of the material. So that is nothing but this del T del B. So that means if you change the magnetic field, so that also depends on what kind of system. So for normal system, it is not the case, but there are certain systems, it is the case. So that means it pretty much depends on what kind of systems you are talking about, what kind of interactions are playing a role. So that depends. So there are certain materials or magnetocaloric effects that you can also measure in terms of specific heat, and you can calculate the magnetic entropy, how much entropy is released. From there also one can calculate the magnetic cooling. So that pretty much depends on the systems. Okay,
Hello.
is it answer your question?
Hello, sir.
Yes, I think I'm asking whether is it did I answer his question? Or did he?
Actually, he has unmuted himself.
Okay.
Well, sir,
Sir, there are some other questions.
Hello. Soham is again unmuted.
Yes, actually, sir, I was asking about, as you talked about very low temperatures for magnetic samples. That is why I asked if layered ferrimagnets can be a good candidate for these kind of measurements, because for the compensation point associated with this kind of materials, we do not get to see the phase transitions, so to speak, but the magnetic, the change in the magnetization is so sharp that the delta S, that is the change in entropy, is very huge. So they can be a suitable candidate when we are not talking about the magnetic phase transition. That's what I asked them, if they are a good candidate.
Okay, that's can be. I mean, the layered materials, I am not an expert. I'm sorry, I'm not an expert, but that can be, if the entropy is really huge, then I think one can think of also in the direction. I mean, one, it can be definitely. I mean, that is one also cross check. People simply do the specific heat, and then you apply magnetic field, and then you see the entropy as you mentioned. But for the layer structures, I don't. So I'm not an expert in the layer structures. But I know people are doing also different type of magnets where they simply look for like very expensive, as you know. If you go to the 4.2 Kelvin, from there, if you can find some material which by applying magnetic field, you can reduce the temperature. That can also use as a very good coolant or substance which you can take the system even much lower temperature.
Thank you, sir. Thank you very much.
Sir, there are some
Yeah, please.
used in squid above 400 Kelvin. This is asked by Dinesh Mahato.
Okay, 400 Kelvin, I don't know. I cannot answer because the measurements which I do at normally 350 to, so one has to be very much careful with the glue. I think 400 Kelvin, I don't know. But if you can use a normal bonder or some, very high temperature and all these things, if your sample permits, then you can use. But from glue perspective, I don't know. For low temperature, I can tell from 300 to even lower temperature, you can use carbon paste, silver paste, and all these things. But at high temperatures, I don't know. I'm sorry.
So here's another question. How many number of cycles can be made in phase change materials?
How many number of cycles?
Yes, can be made in phase change materials.
Change material means, I mean, so the question is not very clear. I mean, phase change materials means in one material, one wants to have more phases like that. So anyway, you don't know. I mean, it's question. So if I understand in a material, so how the different phases will change, that pretty much depends on what are the parameters you are dealing with. Like you have a very good guess. Let's say what kind of interaction. Like for a magnetic system, you can also think of as a magnetic phases. But if you have other systems like where you can tune with pressure, but how much pressure you need, that pretty much all depends on your energy scales, either magnetic or some other energy scales. Then you can tune your systems accordingly. So one materials you can have multiple is also fine, but maybe it is there sometimes like the Scarmian phase which I showed in one of the slide, that we don't know actually. People didn't know, although this material is very old, but suddenly people found that very within few millitesla that phase is appearing. But when we apply magnetic field, we don't go to this very small field, very high field. So that's why normally you don't see. So there are certain phases, maybe it is there, but one has to have a very good, guess or a very good physics you should know. Or sometimes people find, by chance and then try to explore more things. So it is like, happens like that.
So can we take some more questions?
Yes, sure. From my side, I don't have any problem.
Question is from Parmeshwar Divangan. Can electrons of Cooper pairs have any relation in their property like spin angular momentum? If they have, then can we do quantum entanglement from this?
Okay, the moment they're becoming pair, so they are pair actually. So you cannot. So they are somehow coupled with the. So that is the main motivation of this electron phonon coupling. So that you can, as I mentioned, so that's why you have to go beyond that Fermi Dirac statistics. You have to go to Bose institution. So you have to treat the whole system as a boson. So that you cannot control. But when you talk about a single electron, that means then you can spintronics, they can tune whatever they want. But when you are in a pair format, then when you are talking about Cooper pair, that is electron and phonon coupling. So that means you have to also all the time this electron phonon coupling. So electron phonon that mixer, you have to treat the system as a boson, total spin, because that the spin is basically according to the Pauli exclusion principle. If the one spin should be down, so then total spin is actually inside it is 0, is equal to 0. So that means you are treating as boson. So so the treating as like spintronics, you treat with this one single spin. You cannot do that in case of a Cooper pair or in case of superconductor.
Thank you, sir. So the question is how superconductors can be used for energy storage. This is asked by Monica Nago.
Okay. Yeah, so energy storage means, so as you mentioned, so if you can, so the practical point of view, people are not, but ideally it is fine. Like you can see at home we are using all the wires, and that means wire has some dissipation. So that means because of some finite, if we apply current to the system, that means you have some kind of resistance, and then you have some dissipation in terms of I square R. So that means what happens? We are keep on supplying the current. So when the electricity is gone, then your power is gone simply. And when the electricity is there, then means at the end of the month you pay your electricity bill. So that means how much power you consume. But if you could replace all these wires and every things in terms of superconductor, so that means what happens? You apply the energy or apply the, let's say, electricity or the current at the beginning. After that, you don't need to give continuous electricity. So that means once you give this one, then your, let's say your whatever bulb or whatever, it glows. I mean, you don't need to supply constantly. So you just apply the energy at the beginning. And after that, it stores there simply. Of course, you have to, has to think there are other mechanisms where the energy can dissipate. That's a different issue, a technological point of view. But in the energy is not dissipating, so that is fine. So that means you can store the energy like that way. And the similar principle people use in the superconducting magnet, for example. Because when you have superconducting magnet, one has to apply, let's say, huge magnetic field. One generates huge magnetic field by applying currents. Then once the magnet is in the superconducting state, you don't need to apply the magnetic the current all the time. You just apply, and then that mode is called persistent mode, and the energy stays there, simply stays there. You don't need to apply constantly. Otherwise, that's why you are saving some, a lot of power. So in that way, one can also, that is the main motivation and the conductivity that can be used also in energy storage. Yes.
Significance of 4-probe technique over 2-probe in order to measure the resistance.
Okay, so that I briefed in a very, very shortly. That is basically in the 4-probe, what happens? So 4-probe is what happens. To answer your question, if you, very simple question is that, answer is that, so if you measure the resistance, very small resistance, the milliohm or something resistance, then 4-probe is ideal, 2-probe no. Now the question is where? So because we apply to current, then 2-probe, if you have a sample, that means at the same point you are applying the current and measuring the voltage, or other way around. And in that way, the contact which you are making, so that resistance you are taking into account. Although it is maybe small, but when you are measuring, let's say, milliohm, and your error bar is some even or of some more milliohm, then you are not getting actually the proper resistance. But in case 4-probe, what happens? Your probes are really different. So at the end, you have 2 probes, the current you are applying, and your voltage you are measuring at the middle, separate probe points, and no current can go through the voltmeter, because it has normally a huge resistance. So that means you are, let's say, not measuring the contact resistance to the point which you are contacting. So in that way, you can also, the measurement is more precise. So that is the definition of the 2-probe and 4-probe.
The next question from Parmeshwar is, can electrons of Cooper, I think, that is asked, okay. The last question, I guess this is electron motion not affected by very low temperature in superconductor? If yes, then why?
Yeah, so the idea is that, of course, first of all these things you see at low temperature, and to enhance the process, as I mentioned, again, the low temperature reducing the temperature again. So when the fluctuations is pretty much, so that try to make the pair, but they are moving very fast. Now you can think theory of gases, but so they are moving very fast randomly, and so when the energy is really reduced, so that magnetic extractions or via phonons, those things are you can visualize, you can observe, and at low temperature that helps when you are the temperature, then those interactions are more prominent, and then you can observe. That is the idea. So nothing else. Then you can study more. Maybe at room temperature the interactions are there, but you cannot visualize, you cannot observe because of the thermal fluctuations.
That was the last question. So if anybody still has any queries, you may please contact.
Correct.
And we're really lucky to have you in this webinar series. So this.
Okay.
Stay safe. Everybody stay safe.
Hello. Hello.
Hello.
So thank you, Professor Manna, for your nice presentation. So with this, we come to end to the first day webinar. Tomorrow, the technical session will start at 10:50 a.m. So please join at 10:50 a.m.